This video explains the basics of thermoelectric coolers and highlights important design parameters when outlining a thermoelectric cooling application. The goal is to know the important parts of a cooling application and to avoid pitfalls in the design. In thermoelectric cooling, Peltier elements are used to control the temperature of some object. During this video and in our documents, we just call it the object to be cooled. Peltier elements are heat pumps which transfer heat from one side to the other, depending on the direction of the electrical current. This allows heating and cooling. The TEC controller regulates the current supplied to the Peltier element according to the desired temperature of the object and the actual measured object temperature. The object can be a sensor or a heat-generating load like a laser diode, which is placed on the so-called cold side of the Peltier element where the heat is absorbed. On the so-called hot side, a heatsink must be mounted to dissipate the pumped heat. Depending on the temperature measurement, the controller calculates the current that is necessary to drive the Peltier element for cooling or heating to achieve a certain target object temperature. Thermoelectric cooling is used in smaller systems where the solid-state nature of the cooling systems outweighs the pure efficiency. TEC modules, also known as Peltier elements, exist in various forms, sizes and performance categories. Peltier elements are characterized by 4 parameters: Qmax, Imax, Vmax and DTmax. They can be found in every datasheet of a Peltier element. These are theoretical figures and they are used to describe the behavior of Peltier elements. A Peltier element has a maximum heat pumping capacity Qmax if the temperature difference between both sides is 0 Kelvin. The current and voltage associated with Qmax are Imax and Vmax respectively. DTmax is the maximum temperature difference across the Peltier element when absolutely no heat is pumped. Nevertheless, this maximum value is never reached in a thermoelectric application. It is given by the manufacturer to characterize the performance of the Peltier module. It's important to understand that the Peltier element will not produce these figures when just supplying enough current. This graph describes the relationship between heat pump capacity on the y-axis, current on the x-axis for different delta T's. As heat is applied to the cold side, the temperature difference is suppressed. In a thermoelectric application, there is always a trade-off between heat pump capacity Qc and temperature difference dT. It is important to understand that only for relatively small delta T, a significant amount of heat can be transferred. Multistage Peltier elements are used when higher temperature differences are needed. If a high temperature difference is produced or a large amount of heat transferred, more Joule heating contributes to the total sum of heat to be dissipated. The power of Joule heating is exponentially proportional to the current driving the Peltier element. To visualize this, we use a Peltier element with a Qmax of 63 watts and operate it at 70% of Imax, what corresponds to 8.4 amps. The module's heat pumping capacity is 15 watts at a temperature difference of 50 Kelvin. We consult another diagram to see that if we operate the module at 70% of Imax at the temperature difference of 50 Kelvin, the heatsink must dissipate 75 watts in total, 5 times the pumping capacity. Therefore, cooling is the critical case of a thermoelectric application. This is because heat must be removed from an object and together with the waste heat produced by the Peltier element dissipated to the surrounding environment. If a heatsink gets too hot, the desired object temperature may no more be achieved. In other words, the temperature difference will get larger. The controller will work against this by feeding more energy into the Peltier element. Nevertheless, this is known as thermal runaway and it is counterproductive since the heatsink will get even warmer with the additional waste heat of the cooler. When you design thermoelectric cooling applications, the coefficient of performance COP plays an important role. The COP is defined as amount of heat pumped per unit electrical power supplied to the Peltier element. This is a plot showing the COP versus current relationship of a Peltier element. Additionally, the optimum curve is plotted in bright green, showing the highest COP. On the left side, we see that the COP is maximum at the lowest temperature difference. Hence we get a high amount of heat pumped per unit electrical power. Therefore, for an optimum performance of the cooling system, the temperature difference between the object and the heatsink must be kept as low as possible. As we can see, depending on delta T, the corresponding COP maximum is at different current levels. With higher delta T, it moves to the right. If we follow the curve to the right, we find out that we must put a lot of electrical power into the system to get only a little heat pumped, what corresponds to a low COP value. We can also observe that higher currents are needed to produce higher temperature differences. Now we go back to the heat versus current graph. To understand the dynamics of a system, we can observe what happens if the ambient temperature changes, and therefore the delta T, or when the heat load is increased. If we operate the Peltier element with a current around 25% of Imax, it is possible to compensate a rise of delta T from point A to B by increasing the current. The heat pump capacity stays unaffected. The heat pump capacity can be increased as well without changing delta T if we move from A to C. If the working point is around 60% of Imax, we need more current than in the previous example to compensate a rise of delta T, point D to E, when the heat pump capacity should stay unaffected. The heat pump capacity can still be increased without losing temperature difference, if we move from D to F. However, if the Peltier element is operated near its maximum current, a change in temperature can't be compensated by raising the current. The transition from a lower to a higher temperature difference would result in a decrease of heat pump capacity. As a first conclusion, we see that we can add design margin by choosing a Peltier element with greater than required heat pump capacity, by designing a system with operating current well below Imax of the Peltier element, or as a third option by oversizing the heatsink or adding a fan to it to keep the hot side temperature low. By applying these measures, a change in ambient temperature or active heat load does not lead to thermal runaway. As a rule of thumb, for temperature differences smaller than 20 Kelvin, the cooling capacity of the Peltier element should be around 5 times the total cooling capacity necessary. Then we operate this cooling capacity with up to 30% of Imax. For temperature differences larger than 45 Kelvin, the cooling capacity of a Peltier element should be around 1.5 times the total cooling capacity necessary. We operate then this installed cooling capacity with up to 70% of Imax. In this chapter, I would like to highlight another measure to increase the system's efficiency: the use of DC current instead of PWM output to drive the Peltier element. To visualize this, we compared a Mierstetter Engineering DC current TEC controller against a PWM output TEC controller available on the market. We made the following experiment. As target temperature for a 1 watt load as object to be cooled, we chose in both cases 10 degrees Celsius in an ambient temperature of 24.5 degrees Celsius. Both controllers fulfill the same need, but in terms of efficiency the difference is quite striking. In case of the PWM controller, 56 watts were used to keep the object temperature at 10 degrees Celsius. This is more than 6 times more compared to the Mierstetter Engineering controller. Since more energy is put in the cooling system, more waste heat must be dissipated. This leads to a higher heatsink temperature, 5 degrees Celsius more in this case, and therefore to a higher temperature difference between the cold and the hot side. The final consequence is that the performance of the Peltier element is reduced in the case when PWM is used. PWM current for Peltier elements should be avoided and the controller with DC current used instead of. Less overall waste heat is generated. The The goal of this part is to know the essential elements of a thermoelectric cooling system and to understand the important design factors which have an influence on the performance of the system. For this purpose, we disassemble a thermoelectric cooler and discuss the parts from which it's built from. If the object to be cooled is relatively small and does not actively produce waste heat internally, its temperature is prone to influences from the surrounding air. In general, objects and the cold side should be thermally shielded or insulated from the environment when possible. This yields more stability of the object temperature and more performance of the cooling system, since external influences are minimized. Sensor cooling applications are an example where this is important. Here we see a laser diode as an object to be cooled. The object temperature sensor is fixed with a thermally conducting glue. In the best case, temperature sensors can be mounted by integration into the object to be cooled and not attached to it. Additionally to the object measurement input, our TEC controllers also feature a heatsink temperature sensor input and an onboard fan controller. As mentioned before, a fan is another possibility to add design margin. The heatsink sensor is used for optimal operation and precision of the thermoelectric cooling application. With forced convection by using a fan, heat dissipation to the environment is better, since the thermal resistance between the heatsink and air is reduced. To be compatible, the fans need to have a PWM control signal input and they should support the same voltage as the power supply for the TEC controller has. Now we can explore the mechanical construction by disassembling the thermoelectric cooler. A convenient mounting option is to clamp the Peltier element between the heatsink and a metal plate. The metal plate, for example made of copper or aluminium, is used to achieve a homogeneous temperature distribution at the object's interface. By using the metal plate, the Peltier element can be fixed and constant pressure is guaranteed. Avoid bending of the metal plate by choosing a plate sufficiently thick and by moderately tightening the screws. However, more thickness of the metal plate results in more thermal inertia. Make sure that enough pressure is applied onto the Peltier element. This also ensures good thermal conductivity. The recommendation for the mounting pressure from the Peltier element manufacturer should be followed. Reduce thermal resistivity and smooth out asperities by using thermally conductive gap filler or grease. Another important point is to avoid heat transfer from the hot side to the cold side by mechanical elements. This can be seen in the analogy of an electrical short circuit, while here, for example, a screw could be a thermal short circuit. This can be avoided by using thermal insulation for screws. A sealant between the metal block and the heatsink acts as a humidity protection for the Peltier element. The hot side with the heatsink should be on top of the system to minimize self-heating of the system. When a sufficiently large Peltier element has been found, we need to select a suitable TEC controller. All of our TEC controllers share some common features. Bipolar output current that allows heating and cooling without mechanical changes, NTC PT100, PT1000 temperature sensor input, high temperature stability, standalone, remote controlled and script controlled operation modes, communication using Open Communication Protocol, API or LabVIEW VI, and fan controller. We have learned that the Peltier element should be powered with maximum 70% of its Imax value, or even lower percentages for small delta T's. With this in mind, we look for a TEC controller that matches the operating current for the application and not Imax. This table shows our TEC controller product line, from 1 ampere up to 32 amperes. After choosing the TEC controller, the configuration of the TEC controller for the temperature measurement must be chosen. Two types of thermistors or sensors are compatible with our TEC controllers. One type are the platinum thermistors. The temperature measurement range is between -220 degrees Celsius and 200 degrees Celsius. For NTC thermistors, the TEC controller has an onboard reference resistor which defines the temperature range. This resistor configuration can be defined upon ordering. The table shows the possible configuration options and the corresponding temperature ranges. This only defines the reference resistor and therefore the maximum measurable sensor resistance, not the NTC sensor type. The sensor can, for example, be an NTC 10K, what means that the resistance of the sensor equals 10 kΩ at 25 degrees Celsius. For the temperature sensor selection, the application and its temperature range dictates the kind of the sensor. Generally, for temperatures from -20 up to 50 degrees Celsius, NTC sensors can be used. For other temperatures and high precision measurements, we suggest to use PT100 sensors. PT100 or PT1000 sensors have the advantages that their characteristics meet international standards. Thus, their interchangeability is good. They have good temperature cycle behavior as well as long-term stability. The temperature range is large, from very low temperatures to high temperatures. NTC sensors have the advantage that they are cheaper than platinum sensors and often they are smaller. However, the downside is that NTC sensors are not standardized and therefore interchangeability is limited. Another disadvantage is that the temperature range is not as high as with platinum sensors. The requirements for power supplies to drive the TEC controllers are simple. The voltage should be high enough and the supply just needs to have an output current high enough for the controller. Otherwise, when the power supply is in its limitation, the controller will shut down with an error. The temperature measurement input of our TEC controllers is highly sensitive to achieve a high measurement precision. However, this makes the input also prone to defects caused by external voltages. Therefore, when integrating the cooling application into a system, one must pay attention to a careful electrical design and wiring. I would like to repeat some important points we learned in this video. There is always a trade-off between temperature difference and heat transfer capacity. Keep the temperature difference between the cold and hot side as low as possible. And always add design margin to your thermoelectric application. Please refer to the product pages of the TEC controllers for more information. Don't hesitate to contact us for customized solutions and detailed information about our products. Thanks for watching and enjoy the other videos.